Let's talk about sorting algorithms. Before sorting algorithms, we have to define what is a sorting. Okay. First, given a list of records from R sub 0 to R sub n minus 1, so we have n records, then each of R sub I has a key value k sub I. So from the previous examples, R sub I corresponds to one kind of structure instance, and k sub I is the key. So in a structure, we have key and the data. So we've seen these kind of things a lot from binary tree or binary search trees. Okay. So k is key and R is an instance. R sub I is an instance including key and data. Or if we use something like a pointers, then this R sub I should be implemented with key and data pointers. But anyway, so we are not talking about the implementation here. So we are talking about the specifications. So we have a key and we have data. Okay. And there is an ordering relations. Okay. So ordering relation on key value. So it should be transitive. I mean, if it is ordering relations, then we should have these kind of properties. Okay, this is quite simple. If A is smaller than B and B is smaller than C, then A should be smaller than C. This is quite obvious, right? So 1 is smaller than 2 and 2 is smaller than 5, then 1 should be smaller than 5. This is ordering relations. Okay. This is actually transitive property. Okay. So it's obvious. And then the sorting is finding a permutation sigma to rearrange the input list to make a new list. This, where this. Okay. So in this case, we actually change the index. Okay. So you can see this sigma 0 and sigma 1 and sigma n minus 1. And then let me take some example for that. So R0 and R1 and R2. Okay, so we have 3 records and I have key and data. Okay, so the key is 2 and data is A. Okay, so it's just a character. And R1 has a key 3 and data is B. Okay, and R2 has a key and data. Okay. So this is our original record, the list of record. And the sorting is actually to make a new list like R sigma 0 and R sigma 1 and R sigma 2. Okay, so in this case, the answer would be so simple. So the first one should be 1C and second one should be 2 and A. And the third one is 3 and B. So in this case, sigma 0 is actually 2. Okay, so this one. So it was 2 and sigma 0 was 2. Okay, and then sigma 1 is 0 and sigma 2 is 1. So we found this mapping function, sigma. So now we have a new ordered list. Okay, good. So in this list, k sigma I minus 1 is always smaller than or equal to k sigma I. Do you see that? So k2, so I'm talking about this one, k2 is smaller than or equal to k0. Okay, because k0 was 2 and k2 was 1. Okay, so we met this condition, so now we sorted. Okay, so with the keys. Okay, so there are 2 different approaches. So first one is internal sorting and second one is external sorting. So as the terminology says, internal sorting means we will sort all the elements in the main memory. Okay, so that's internal. So external sorting will sort all the elements in the secondary storage, so like hard disk, because sometimes we have really long list In that case, our main memory is not enough to hold all the elements, so that we have to use a secondary storage. So we are going to talk about internal sorting a lot, and at the end of this chapter, we're going to talk about external sorting approach too. So recently, we have a big data a lot. So when we have a big data, then if you want to sort this big data, then the main memory is not usually enough. Then if you really want to sort, then probably you have to use this external sorting approach. Then next one, stable. So when the sorting is stable, okay, when we say, oh, this sorting algorithm is stable, it means this. If I is smaller than j and ki is equal to kj, then ri precedes rj in the sorted list. Okay, so this statement might be a little confusing. Let me give you one example. Okay, so we have 2, 3, 2, 1. Okay, so this is our original list. Okay, so to distinguish, let me put another superscript here. Okay, so this is 1, this is 2. So it means this is the first 2 and this one is second 2. Okay, so if when we sort this list, it is 1, 2 first, 2 second, and 3. Okay, so we don't change the order of these two, then this is a stable sorting algorithm. But sometimes, some sorting algorithms change this order, like 1, 2, second 2, and first 2, and 3. So this is not a stable algorithm. Okay, this one is perfectly fine. This is perfectly fine sorted list, right? So 2 is 2, fine, but we just changed the order of these two elements. Okay, so in this case, this algorithm is not stable. So we are going to use this property later. Okay, some sorting algorithms are stable, some sorting algorithms are not. Now, before talking about the sorting algorithms, let's talk a little bit of motivations. Okay, so here's an example. We want to do list verifications. So we want to check if these two lists are the same. So if they include the same kind of elements. Okay, maybe one list might have duplicated keys. Okay, so they might have different lengths, but they might be the same. They could be kind of identical. Okay, so we want to compare these operations when the lists are sorted and when the lists are not sorted. Okay, so by comparing these two cases, then we can see the effect of sorting. Okay, so we have a list 1 and list 2. Okay, and then we want to search and compare each element in list 1 and the list 2. So what should we do here? If the two lists are not sorted, okay, and then without sorting, let's try list verifications. Okay, then we have to check if this element is in this list. So this one is not sorted, then we have to check this element and this element and this element. We have to compare this element with this one, this one, this one to this one. So if the C is the same as A, then we can stop there, but in a big O notations, okay, then we have to compare n times. Okay, then how about B? Basically, we have to do the same thing. So we need n operations, n comparisons, and for C and so on. So basically, in the big O notations, we need these computations. Okay, so that's what we do without the sorting. So n times n. But we can do this after sorting. Okay, so let's say we already sorted, okay, these two lists, and then we can check these two elements, and then we check the next one and the next one, etc. So basically we can check m times n plus n. Actually, depending on the scenario, it could be like min m n or max mn. Okay, So depending on the situations, so sometimes we need this, or sometimes we need this, sometimes max, m, n. Okay. So now let's talk about the complexity. So we said, okay, this list verification is after sorting. So how much computation cost do we need to sort? So let's say this is time to sort n and time to sort m. Okay, to sort this list and to sort this list. And after sorting, yeah, we need n plus n computations, or mean or max, doesn't matter. Okay, and then usually the time complexity for sorting is n log n. Time complexity for sorting m elements is m log m. Okay, so we'll talk about this computation cost later. When we talk about the sorting algorithms, we'll see how come we get these numbers. Okay, so for now, just believe me. Time complexity for sorting is n log n. So we have a plus operation. So in a big O notation, we have to take the dominant component. So we have a max here. So it could be n log n or it could be m log n depending on the length. Okay, so that's what we have. So compared to the previous one, in the previous slide, we had m times n. Okay, so in the big O notation, it was m times n. Now, after sorting, if we do this list verification, then let's say n is bigger, then it is n log n. So compared to this one, so we have n here and here. So instead of m, we have log n, which is much faster than m. That's the beauty of sorting. Okay, it looks like we have one more step. Like instead of comparing directly, we have a sorting process. Okay, and then after sorting, and then we check. But still, that is faster than before. So now we have to study sorting algorithms, right? So in sorting algorithms, we have lots of, as a sorting algorithm, we have lots of options. So insertion sort and quick sort and merge sort and heap sort and radix and external sortings. Okay, and in these sections, we'll talk about the computation cost about the sorting algorithms. Okay, and as I said, this one is external sorting. Other than that, these are pretty much internal sorting. So basically, these sorting algorithms work in the main memory, but this one works with hard disk. And we'll talk about this one later, but no one algorithm is best for all apps. So it depends on the situations. It depends on how the lists are unsorted, okay, how they are distributed. So depending on the situations, then insertion sort could be best, quick sort could be best, and merge sort and heap sort, radix. So depending on the situations. So basically, we don't know which one is the best in general, but in general, quick sort might be fastest in general, but not for sure. Okay, so that's why we call it quick sort. It's quick, it's faster than the others in general. Okay, there's no guarantee. Okay, before talking about the real sorting algorithm, like insertion sort or quick sort, etc. So let's talk about some simple sorting algorithms. Selection sort. We already talked about this one before, but this one will provide kind of the baseline. So if we have some naive sorting algorithms, then we will see what kind of computational cost we need. Okay, and then if we have a quick sort, then how much improvement we can get based on a little complicated algorithms. Okay, so selection sort. So we have n integers. So basically, we are going to talk about just the keys here. Okay, so we don't care the data part that much when we talk about algorithms. Okay, so the simple solutions. From those integers currently unsorted, find the smallest and place it next in the sorted list. So selection sorting is really easy and simple, but computationally it's not that cheap. So let's see, we have 5 numbers here. So 6, 5, 3, 4, 2. So this is not sorted. Then what should we do? So first, find the smallest. Basically, we sort this list in an ascending order. Okay, so from the smallest one to the largest one. Okay, so find the smallest one first. So 2 is a small, so since 2 is the smallest one, swap. Okay, so now 2 is here and 6 is here. So consider this part as a sorted list, and this part, okay, this part is sorted and this part is unsorted. And from this unsorted list, then we apply the same thing. Okay, so find the smallest one, which is 3, and swap 3 with the first one in this unsorted list. Okay, so swap these two. So now we have 2, 3, and these parts are sorted. Okay, now we have unsorted list here. And then from this unsorted list, find the smallest one, 4, and then swap this one with the first element of this unsorted list, which is 5. So swap. So now we have a sorted list here and unsorted list. From this unsorted list, find the smallest one, which is 5, and swap this 5 with the first element of this unsorted list, which is the 5, which is 5 itself. So we swap. It means basically do nothing. And then we have a sorted list and we have unsorted list. If the length of the unsorted list is 1, then we stop. Okay, we already sorted. Done. This is selection sort. This is quite naive and simple to understand. Okay, that's it. So let's try to implement this selection sort. We already talked about this one. Okay, so basically we have a 2 for loop. This for loop goes from the leftmost one to the rightmost one in the previous slide. Okay, and then with this for loop, we are going to find the smallest one. Okay, and then there is a swap function here. So I think this function is really easy to follow and it's easy and simple to understand. So I think this is enough. Okay, and let's talk about the computation cost. For the first for loop, it goes from 0 to n-1. So we have n iterations. Okay, and how about the second one? It goes from i+1 to n-1. So sometimes if I is 0, then it goes from 1 to n-1. If I is n-2, then it goes from n-1. That's it. But still, when we calculate the computational cost, then basically it takes n. Do you see that? So on average, let's take some average. So for the first iteration, we need n-1 times iteration. For the last time, we have just one iteration. This is just one iteration. So when we take the average, then we have n/2. Okay, but in the big O notation, we ignore the constant. So we need n times, and we need n iterations. So we have one n iteration here and another one here. So basically, n squared is our computation cost. And the swap means nothing here. Swap takes some constant. Okay, so swap takes some constant time. So we ignore that constant. Okay, so n squared. Even for the best case, right? Even for the best case, we have to iterate from the leftmost to the rightmost. Okay, so the first for loop, we need the first for loop, and for every iteration, then we have to find the smallest one. Okay, so we are not sure that the unsorted list is sorted. Even though the unsorted list is sorted, but still we have to check all the elements to find the minimum element, the smallest one. Okay, so we need this for loop even when the given list is already sorted, but still we need n squared computation cost. Okay, so selection sort is really simple and easy, but in a computation cost-wise, this is not the best. So nobody uses the selection sort. Okay. And the next one is a bubble sort. So bubble sort is another kind of simple algorithm, naive simple algorithm that nobody uses. Okay, but let me explain how it works. So maybe you can get some idea from these sorting algorithms. Okay. So basic idea is quite simple. So we have, let me explain this one with the example. So we have this unsorted list. Okay. Then first, we check these two. Okay. Then 5 is larger than 1, then we swap. We get this one. Okay. So from this list, so we copy this one. From this list, then we check this one. And 5 is greater than 4, so we swap. Okay, good. And then next, we check this one. Oh, 2 is smaller than 5, we swap. Okay. And then we check this one. Oh, 5 is smaller than 8. Just leave them as they were. Okay, so we are done. So this is one iterations. In this iteration, we have iteration like from the first to the last. Okay, so we have a two loops. Okay, and then that's not it. Oh, basically this is just one iteration. Sorry. So from this one to this one. Okay, just one iteration is fine. Okay, for one for loop, and then this is not it, because look at this one, 4, 2. Okay, so we have, this is not sorted yet. Now we have to do this one more time. Okay, so 1, 4, 1, 4, fine, and 4, 2, we have to swap. Okay, then 4, 5, okay, that's good. So we don't have to do anymore. And then 1, 2, that's good, and 2, 4, that's good. Okay, so in these iterations, we don't check this one. Okay, and in this iteration, we don't check this one, because think about this, the first iterations. So in these iterations, after these iterations, the largest element will be the rightmost element. Okay, so basically we check two elements and two elements, two elements and two elements. So the largest element will be the rightmost element. Okay, so we can consider the rightmost one as a sorted list already. So we have to focus on this left 4. Okay, and then after these iterations, then we can consider these two elements as a sorted list already. So we can focus on this. Okay, so that's the algorithm of bubble sort. So basically we need two for loop. Okay, so the first for loop is corresponding to this one, this one, this one, and the second for loop corresponds to this list and this list and this list. And every time we check if the current one and the next one. Okay, so in this example, when the j is 0 and j plus 1 is 1, so we compare 5 and 1. And in the next iterations, we compare 5 and 4, and 5 and 2, and 5 and 8. So we compare the current one with the next one. And if the current one is larger than the next one, then we swap. So this is the algorithm of bubble sort and implementation of bubble sort. So it's like a selection sort, right? So selection sort and bubble sort, these two sorting algorithms are really simple, but computationally terrible. Okay, so here is a main function for practice. So in this main function, you can get the number of elements and the method. Okay, so let's say, oh, I want 5 elements, and the method is maybe a bubble sort, then 5 and b. Okay, so method is a character, and then we allocate the memory space for 5 elements. Okay, time starts from here and it ends here. Okay, so we can check how long it takes to sort, and then with this for loop we get some numbers. So since we said, okay, the input, the count is 5, so from 0 to 4, we generate a random number, and this key is just random number, and we put some data. Okay, so in this case, a string. Basically, list is element is a structure with key and data. Okay, now we check the time to sort. So we have a bubble sort here. So bubble sort will sort this list. Okay, and then we can print out the time. Okay, it left the time here. And now with these main functions, you can check how much time we need to finish bubble sort. So whenever you learn some sorting algorithm, then implement that, and you can check that sorting algorithm. You can actually measure the time to finish the sorting algorithm. So you can compare these sorting algorithms. Okay,